Hi, this is Nicolas Sopiadis, and welcome to my project presentation on a single GPU language model for Linux documentation. If you have ever used Linux, you know that it is free, very customizable, and especially hard for beginners, but it is quite well documented. You can find documentation in man pages, TLDR, a shorter form of man pages, various wikis and forums, and even videos. However, these videos tend to not delve into very advanced topics. If you face a specific problem and require a fast solution, searching for that solution can become very inconvenient. To make our lives easier, we'll have two requirements: being able to ask someone your questions and getting a quick answer, and using all our available resources. This leads us to a locally trained language model. The obvious answer is ChatGPT and its ancestors GPT-4, 3, and 2. GPT stands for Generative Pre-trained Transformer. It takes a series of tokens as input, and it tries to predict the following tokens. This makes it lack context awareness. After a bit of researching, I found the not so obvious answer: BERT. BERT stands for Bidirectional Encoder Representations from Transformer. Bidirectional means that each token does not only take into account the following tokens, but also the previous ones. This makes it more context aware and better suited for our application. Similar work has been done in the Cramming paper, in which they trained a BERT model on a single GPU in 24 hours. Similar work has been done in the Cramming paper, in which they trained a BERT model on a single GPU in 24 hours. The similarities between the Cramming paper and my project are that they both use consumer hardware. They used an RTX 2080 Ti, whereas I used an RTX 3060, which is about half as fast. Due to time constraints, I have about 2 hours to train each model, and of course that leads us to a smaller model size. The training data was gathered from the Arch Linux wiki, man pages, a few select Linux-related Wikipedia articles, and all of the Linux kernel documentation. I learned that gathering good data is difficult, and it requires a lot of preprocessing. The data preprocessing steps I took are: removing unrelated entries, removing most of the non-English text, only keeping files with size larger than 1 kilobyte, and I split the data into 90% training data and 10% validation data, ending up with 170 MB of training data and 17 MB of validation data. Feeding the data into the model is done using a scheduler, which streams the data, so it does not keep a copy of the whole dataset in memory due to memory constraints. It reads each file in 1 BB chunks, tokenizes, and emits a 128 token sequence. The tokenization is done by using the BERT tokenizer fast by Hugging Face. Training a BERT is slightly different to training a GPT. In a BERT, you remove some of the tokens and let the model fill in the blanks using nearby tokens as context. This process is called masking. For the masking, I used the same masking process as the Cramming paper. 25% of the tokens will be masked. The masked tokens have an 80% chance of being replaced with a mask, which means they will be removed completely, a 10% chance of being replaced with a random token, and a 10% chance of remaining unchanged. Another difference compared to the Cramming paper is that I will use multiple epochs due to the smaller dataset size. In the Cramming paper, they trained the whole model in a single pass. Moving on to model parameters, the Cramming model uses 12 layers with a total of approximately 110 million parameters. The data comes to around 3.3 billion tokens, giving us a token per parameter value of 30. The Chinchilla scaling law states that the optimal tokens per parameter are about 20. More than that, and you have diminishing returns. My model uses 6 layers. The data is about 170 MB, giving us 50 million tokens per epoch. Using 10 epochs and the optimal TPP of 20, we get a requirement of 25 million parameters. I decided to test two models. The first uses half of that, coming to about 13 million parameters, and the second uses the full 25 million parameters. My model is a decoder-only transformer with 6 layers, a hidden size of 256 for the 13 million parameters and 512 for the 25 million, 6 heads, a feed-forward network of 1024 or 2048 neurons. I use sinusoidal positional embeddings, similar to the Cramming paper. Similar to the Cramming paper, I use sinusoidal position embeddings and skip and similar to the Cramming paper, I use sinusoidal position embeddings and skip the similar to the Cramming paper, I used sinusoidal positional embeddings, and in order to save on memory and training speed, I used no query key value biases and skipped the non-linear output rejection. Delving deeper into the transformer block, again following the Cramming paper, I used pre-layer normalization. The process is as follows. First, we have a normalization layer, then the multi-head self-attention layer, then the residual, then again a layer normalization, followed by feed-forward network, which is activated by a GLU activation function, and finally another residual layer. Due to memory constraints, in order to train the network, I used micro batches of 96 tokens with dynamic accumulation. Following the Cramming paper, on my first attempt, I used their values, starting with 21 accumulation steps, giving us an effective batch of 2000 tokens, and ramping to 85 accumulation steps, giving us an effective batch of 8000. The batching is the accumulation reaches its maximum at about 60% of the training. The first attempt started at 21 accumulation steps, giving us an effective batch of 2000 tokens, and ramped up to a maximum of 85 steps, resulting in an effective batch of 8000 tokens. This maximum is reached at 60% of the training. On the second attempt, I tried using different values to get a more aggressive learning curve. The optimizer used was the Adam W optimizer with the same weights as the Cramming paper. Since I will not use a single training cycle but multiple epochs, I opted to use a learning schedule of cosine decay with 10% warm-up. Further optimizations include using mixed precision floating point numbers with no measurable difference in performance, using PyTorch kernel parameters and compiling the network with just-in-time compilation, resulting in a 10% performance increase, and finally dropping the query key value biases, resulting in another 10% performance increase, for a total of 20% performance. Here are my two training attempts. The first attempt uses the smaller network, with the hyperparameters being directly copied from the Cramming paper, and the second attempt uses a larger network with parameters that result in a more aggressive learning rate. Here are the results of the models after being trained. I deliberately let them train past the 10th epoch to see if the results would be better or worse. The metrics used are top 5 accuracy, perplexity, top 1 accuracy, and of course the validation loss. Starting with the top 5 accuracy, we can see that both models have an accuracy of less than 1%, with the larger of the two models having slightly better accuracy. Perplexity can be easily thought as how sure the model is about its answer. We can see that both models hover around 10%, 10 to 15%. The top 1 accuracy of the first model is less than 0.5. The top 1 accuracy is the top 1 accuracy of the first model is less than 0.5, and of the second model is around 0.5. Terrible. Lastly, we can see that the loss hovers around 3% for the first one and 2.5% for the second one. From these results, we can see that the model is learning something, but what it is learning is not the desired function. Here are a few samples. As you can see, both models cannot answer any question, answering with gibberish. After analyzing the results, I came to the conclusion that the failure point is the dataset. The dataset is very small and consists in large part of documentation that is very abstract and tailored to humans. Furthermore, both models are underfit. This can be concluded by the fact that the more aggressively trained model resulted in slightly higher scores. Some possible improvements would be to use a larger dataset, to use a cleaner and more training-friendly dataset, possibly more aggressive learning, and instead of pre-training the model directly on the Linux documentation, to pre-train it on a more general dataset and fine-tune it using the more specific Linux dataset. Thank you for your attention. If you have any questions, feel free to contact me on my email, and you can check the code and the whole project on my GitHub.